Welcome back. In this lecture, we will look at the last topic relevant to thermodynamics of electrochemical system, with respect to this course. This topic are interrelated. We have used this word activity often, and I will talk about that more in this lecture. And a particular model for computing activity, which is the Debye Huckel theory. In the previous lecture, we had introduced liquid junction potentials. Liquid junction potential were kind of special because before this potential, all our models for electrochemical potential was based on thermodynamic arguments. But in this liquid junction potentials, on one side, you have a material which is higher in concentration. On the other side, you have lower concentration. And there will be diffusion because of difference in mobility between the ions. There's charge accumulation, and hence a potential gets generated. That's called liquid junction potential. So this potential is inherently because of rate processes, transport rate processes. So that's what makes it different from the thermodynamic potentials mentioned before this particular topic. We can measure these liquid junction potential. We are given the framework for measuring these potentials. This depends upon the mobilities of different ions and other factors. Okay, so, but what you should be aware of is the magnitude of liquid junction potential is rather small. It's not zero, but compared to the magnitude is small. So it by itself, it may not lead to generation of Faraday reaction. I mean, just because there's a liquid junction potential, you may not expect an electrochemical reaction. Okay, so because the magnitudes are relatively small compared to what you can achieve via an external power source and so on. And we also try to address other questions relevant to electrochemical thermodynamics. For example, if you ask how to quantify the change in potential with respect to temperature, you have to go back to relationships that you see in chemical thermodynamics. How does free energy change with temperature? You can connect the change in free energy to potential and answer the question how to think about dou U by dou T. Okay. And we also introduce again what is a Sol bridge. This is a very critical component of any electrochemical system. Often, if you are working in a lab, you should know how to prepare a Sol bridge, what goes into the Sol bridge. It serves multiple purposes, two main purposes being that it helps in maintaining electroneutrality even when there is a Faraday reaction occurring in these two chambers. And it also helps in separating these two chambers. Separating, that is the zinc contents is isolated in this chamber and copper content is isolated in this chamber. In that way, it is separating, but it also provides a continuity in terms of certain flow of ions across the Sol bridge. Okay, so the working of a Sol bridge, you should know how to explain the working of a Sol bridge. What are the you can also explore what are the components that go into the Sol bridge. There can be different kinds of Sol bridge here, as opposed to this kind of an arrangement. Here also we have a Sol bridge, and we introduce this cell, so-called concentration cell, because the potential that is generated is just because the difference in concentration of the salts. On one side, you have greater concentration of a particular salt, in this case, a salt of copper and chloride. On the other side, you have lesser concentration. Because of this, there is a flow of conventional and electronic current. We discussed this in some detail in the last lecture. We can also write the thermodynamic potential, electrochemical potential that is generated from such a system And again, the value of these potentials are relatively small compared to what one may see in a battery or by the use of an external power source. So these are not zero, but still they are smaller quantities compared to what you typically observe. We also introduce a very important topic of sensors. This is a very important topic, especially in the context of biomedical devices, environmental pollution. A lot of complexity that goes into the working of a sensor. We can't really do justice to all the details related to sensors, but we mentioned that working of these sensors critically depends upon an ion selective membrane. Okay, so this electrode is called an ion selective electrode. This membrane is an is selective to one particular ion. So why is that so? So that typically depends upon two things. One is that the membrane has a particular wall charge. For example, in this case, if the wall charge is a positive quantity, it would selectively allow only anions to pass through. It will reject cations, and it will only allow for anions. In addition to such kind of selectivity, there is also a size selectivity involved, size and charge selectivity involved. Okay, so not all anions are allowed to pass through. Only certain anions are allowed to pass through. That will also depend upon certain size constraint. These kinds of membranes are present in biological systems also. The arrangement that allows for ion selectivity in biological systems is really explicit. Okay, so there is, it can sometimes allow for larger ions to go through, but rejecting smaller ions. That is, can be very counterintuitive. These are called these proteins, which allow for such operation. They are called ion channels. They are present in the biological cell membranes, and these are also present in typical electrochemical cell. The most famous ion selective membrane is in electrochemistry. It's called the Nafion membrane. It is selective to proton. Okay, and it is a negative wall charge. So how does this ion selective membrane work? Supposing you want to sense a particular ion. Okay, so the purpose of this ion selective electrode is to sense a particular ion. Okay, so that ion which has to be sensed has to be passed through this membrane. That is, this membrane is selective to the relevant ion which has to be sensed. So when you insert an ion selective electrodes into a test solution, the test solution contains the analyte, okay, with whose concentration, the concentration of a particular ion has to be analyzed. So when you insert such an ion selective electrode, there's an equilibration of chemical potential. That is, the chemical potential of an ion inside the membrane is equal to the chemical potential of the ion outside the membrane. So if you remember the definition of chemical potential, in this case, the electrochemical potential, there are two components. There is a component which is the chemical component, depends upon the activity of the ion, and there is a component which is the electrical component. So when the electrochemical potential gets equilibrated between the inside of the membrane and the outside of the membrane, so mu I here is the same as mu I outside. Based on such a balance, we can develop an equation, something like this. Okay, so this is a straightforward substitution. Overall, what you have to appreciate is that when you dip an ion selective electrode, there is an electrical signal. That is, there is a potential that is being generated against an ion selective electrode and some reference electrode. The magnitude of the electrical signal that is generated is correlated to the activity of the ion in the test solution. So if you can develop a correlation, a chart, okay, a calibration chart, wherein different electrical potentials are calibrated to different concentration of the test solution, you can use this ion selective electrode to detect an arbitrary concentration. Okay, so what is very important to notice is the electrical response can be correlated to the concentration of the ions in the test solution. Then we move on to certain other aspects of electrochemical table, the series of electrochemical potential that you often see in many electrochemical textbooks. So we introduce additional complexity, one wherein a particular element, in this case ion, can exist in more than one charge state. In this case, it can exist as Fe2 plus and Fe3 plus. Supposing we know the electrochemical potential between Fe2 plus 2 electron Fe, that is one potential. Let's say this is the value. So there is somewhere here. If the values vary a little bit from source to source, but that potential is here. So there can be another redox potential between Fe3 plus 3 electron in equilibrium with Fe. Okay, so if you know these two values, we can effectively calculate when this transition will happen. When you keep increasing the potential to more and more anodic in the anodic region, that is, make it more and more positive. First, you would see Fe2 plus. That is, if you're more positive than negative 0.41, okay, you would see Fe2 plus. And then as you increase the potential to more positive, in the more positive direction, that is the anodic direction, you would also see a transition to a higher oxidation state. That is this number. Okay, so to get this number, you have to first appreciate this is indicative of certain thermodynamics. Okay, and the other number that is indicative of the thermodynamics of Fe3 plus 3 electron in equilibrium with Fe. So knowing those two numbers, I can get this number. This is what we discussed in the last class. So this kind of a diagram is called a dominance diagram. In this diagram, the dominance diagram is a function of only the potential, because there is only electron transfer in this electrochemical reaction. But in some other cases, we discussed the example of zinc. There can also be both electron transfer as well as proton transfer. So, and such a dominance diagram is often called the Debye diagram. So it has two coordinates. One is the equilibrium potential, just like this coordinate, and another is the coordinate which is indicative of the chemical potential of protons, which is the pH. So there are three distinct lines. One is a horizontal line, a vertical line, and a line which is neither horizontal or vertical. The horizontal line tell you the transition involving only electron transfer. In this case, for example, this boundary gives me the equilibrium between Zn2 plus 2 electron in equilibrium with Zn. Whenever you see a vertical line does not involve any electron transfer. It is purely a chemical equilibrium. Okay, there's no electron in either the reactants or the products. It's a chemical equilibrium. And whenever you see a line which is neither vertical or horizontal, that involves both protons and electrons. That means what I mean is electron and protons has to be present either on the reactant side or on the products. Okay, that's when you see such a line. Always, whenever you see Debye diagram, you will see two lines. These are in an aqueous Debye diagram. That is, why is this two lines important? Is it tells, it is indicative of the stability window of water. Above this potential, water is no longer stable. Water will get oxidized to O2 and to protons and so on. Below this particular potential, water will give rise to hydrogen evolution reaction. Okay? So beyond this, hydrogen evolution reaction is thermodynamically favorable at this particular pH. Beyond 1.23, at this particular pH, oxygen evolution reaction is favorable. So another point we emphasized is that all these dominance diagrams, both this one and this one, are indicators based on thermodynamics. We are not talking about any kinetics here. Okay, there's no measure of activation barrier in this diagram. Okay, so even though when something is thermodynamically possible, it might not be kinetically possible. The example we quoted is the lead acid battery. If you look at the potential that you can get from a lead acid battery, it is more than 1.23, and it's an aqueous battery, right? You don't see oxygen evolution and hydrogen evolution all the time. That is because the kinetics of oxygen evolution reaction or either of these two reactions is suppressed in the electrodes relevant to the lead acid battery. So we will discuss these kinds of issues more when we get into electrochemical kinetics, which will be the topic from next lecture. Okay. Coming to the central topic of this lecture, which is the activity. What is activity? Okay, so when you have a word called activity, which seems like a colloquial word, okay, there should be a reason why people use this term, a colloquial term, to indicate a technical concept, right? So there is a sense in using such a colloquial term. Activity is indicative of two things, okay? It is indicative of how reactive that chemical is, or it is indicative of how easily it will get transported to some other region. So if a chemical species has greater activity, that means it is more reactive, or it has a greater tendency to get transported to some other region. If you discuss chemical reactivity and, let's say, chemical transport, diffusion, migration, and so on, all these systems, reactive systems, and chemically when there's transport in a chemical system, both these things can be discussed using chemical potential. Activity is another way of describing the same system. Okay? In some ways, there are two equivalent descriptions. One description is based on chemical potential. Another description is based on activity. Okay? So in some ways, activity is, there's one-to-one correlation between activity and chemical potential. If you remember the definition of an electrochemical potential, it has two parts. There's the chemical potential and the electrical potential. So here we have the activity in the chemical potential. So that's where we had introduced activity. And this you must have seen in your chemical thermodynamics classes. Here I'm just throwing in a preliminary definition. The objective of this definition is that activity is a dimensionless quantity. It goes into a long term, therefore it is dimensionless. It is the supposing you are discussing the activity of a species I, it is the ratio of the fugacity of that species and the fugacity of that species in its pure state. Okay, so we have just substituted one definition with another unknown term, activity by fugacity. So it's not such a very helpful definition unless we tell how do we compute these fugacities. Okay, so this looks like an abstract definition, but we'll see how do we understand how to operate, implement this definition. The best way to understand fugacities and activity is to take typical systems. Okay, there are two two broad systems we'll be addressing, gases and liquids or electrolytes. Okay, so if you go to a material science class or a metallurgy class, the chemical equilibrium involved in which you see in, let's say, alloy thermodynamics, alloy phase equilibrium, there all the phase equilibrium principles will be determined using chemical potentials. As we mentioned, activity is equivalent to chemical potential. So description of alloys often involves utilizing the principles of activity for different species that goes into the alloy. That won't be the topic of our discussion here. We'll be mostly focused on how to understand the activity of electrolytes. But for just pedagogical reasons, we will introduce gases also. So a critical aspect of the definition of activity is how do you use the standard state? Okay, how you choose the standard state. This is the standard state in our definition. So that there's a lot of subtleties involved in choosing a standard state. This is not a class on chemical thermodynamics, so we won't have time to go into all the details, but you should be aware of these details when you use activity in your research. Okay, so there are some deeper issues. We will just allude to these issues in this lecture. Activity and fugacity is a great concept introduced in, I think, early part of 1900s by physical chemist G.N. Lewis. You must have heard about Lewis in the Lewis dot structures that you saw in your high school chemistry. Lewis is probably one of the greatest chemists who did not get a Nobel Prize. He formulated these principles to discuss principles of chemical equilibrium. Let's move on. Let's look at a concrete example of activity in gases. As I said, this is the activity of a chemical species I, fugacity of that species and fugacity of that species in the pure state. So the fugacity of that species is a product of three quantities. This is the fugacity coefficient. This is something which you probably know. This is the mole fraction of the species in the gas phase times the total pressure. In this discussion, we will assume that fugacity coefficient for that species is 1. In essence, we are saying that species behaves as an ideal gas. There's no interaction within the gas, between the gas molecules, and between that species I and any other species. Okay, so this assumption is just equivalent to saying it's an ideal gas mixture. So then this can be implemented into this definition. So you have mole fraction times the total pressure divided by the standard state. The standard state in this case is this number. Okay, it's equivalent to 1 atmosphere. Okay, so this would make the activity as a dimensionless quantity, and with respect to this particular number, we can talk whether that species has higher activity or a lower activity. Let's move on to the system that is most relevant for our discussion of electrochemistry, which is the activity in liquids. So what we see here is on the y-axis, the activity of a species I. On the x-axis, we have the concentration of this species. So this red line is where AI is equal to CI. So there are two systems that are indicated here. This green curve is a non-ionic solute. Okay, this is still, let's say, dissolved in water. Let's say water is, we are talking about, let's say, an aqueous system. Let's say you dissolve glucose in water. That's an example of a non-ionic solute. What do you see? You see that the deviation from AI is equal to Ci is less in the case of a non-ionic solute. So for such a system, you can approximate the activity of that species as Ci divided by C naught, where C naught is a standard state. Okay, so you take some standard concentration C naught here, and you can discuss the activity of that species. Another point to notice is that at low concentration, okay, so when you keep decreasing the concentration, both the ionic state, ionic solute, and the non-ionic solute, for both these systems, AI is equal to Ci. Okay, the deviation from this red line kicks in only at higher concentration. It kicks in earlier for an ionic solute. Okay, so we will look into the reason why that is so. Okay, so for an ionic solute, you define the activity in terms of an activity coefficient times Ci divided by C naught. Okay, so again, we have substituted one unknown with another unknown. Here the unknown is activity coefficient, which is gamma I. Again, C naught is some standard concentration. So let us start thinking through the underlying principles. Okay, so what do we exactly mean by deviation from this linear line? So when you have a linear line, what it indicates is every component behaves independent of every other component, right? That is, when I'm having an ion, let's say of this species, each ion behaves independently of every other ion. That means what? Each ion doesn't really know the presence of other ions in the solution. That's why even when I add more and more ions into the solution, my activity doesn't change. It shows a linear behavior. When would that happen? That would happen when the ion or the solute-solute interaction is very less. Because if you, in the non-ionic solute, it is not a charged species, each solute does not really see, the capability of each solute to see another solute molecule is very less, okay, because these interactions decay very quickly, therefore, in terms of distance, okay. So the presence of the solute is only felt only in the regions close to that solute, okay, in a non-ionic solute. But when you have an ionic solute, these electrostatic interactions decay slowly. That is, these are longer range interaction compared to other chemical interaction that you had in a non-ionic solute, because of which the interaction between ionic solute is larger. Therefore, even at a lower concentration, the ionic solute will sense each other. Each ion will sense the presence of another ion of another solute ion, the ionic solute ion. Okay. So there are two kinds of interactions. Okay, so that are present when you are discussing these things. One is the ion-solvent interaction, okay, which will determine whether, or the solute-solvent interaction, which will determine whether the solute is soluble in that particular solvent. Okay, we are not discussing that interaction when we are talking about deviation from this linear line. When we are discussing deviation from this linear line, we are discussing the solute-solute interaction. Okay, the greater the solute-solute interaction, the greater is the deviation from this linear line. Okay, so the take-home message here is to know the activity of an ionic solute. I should have a good model for gamma I, which is the activity coefficient. just to get a closure on activity of liquids, the liquid here contains two parts. One is solute, that's what we discussed in greater detail. There's also this other component. Solvent is the dominant component, right, in a solution. So for the activity of a solvent is typically given by this fugacity of the solvent by the fugacity of the pure solvent at that temperature. So at that temperature, this is the dominant component. You can take that fugacity of the solvent to be the vapor pressure of the solvent divided by the vapor pressure of the pure solvent at that particular temperature. All right. That is the definition we can use. And it goes without saying that if you have a pure liquid, its activity is 1. Okay? This we have mentioned in a previous lecture too. What is, let's look into this in greater detail. Okay, so we said that the activity of that solute is given by this definition. The standard state for this definition is an ideal 1 molal solution. So we will take this to be 1. So this quantity will reduce to this quantity because we are taking this to be 1. We'll see why that is so. First, let's understand what we mean by an ideal solution in this case. Okay, so these are all constructs, okay, which are not attained. We'll see why this is not attained, and we'll see what is and what we can do to utilize these principles in practice. What we mean by an ideal solution is that we have only ion-solvent interaction, and there's no ion-ion interaction. There's no solute-solute interaction because we are talking about ionic solute. We are talking about ion-ion interaction. Okay? So, as I said, when is there no ion-ion interaction? Only where the molality. Okay, so Mi here is the molality. I suppose you know from your high school why you use molality. What is the advantage of utilizing molality compared to molarity and other units for measuring concentration? Here we have when molality goes close to 0, it tends to 0, then the concentration is very less. That means the ion-ion interaction is very less, just because the ion, the distance between the average distance between each ion is less, and each ion doesn't sense the other ion. Okay, because of that reason, the ion-ion interaction is very less. In that case, AI will be same as Mi in this case. Activity coefficient is 1. Okay, that is if you plot the concentration against the activity, there'll be a linear line at low concentration. So we know one limit. That is, even without any quantitative theory, just from physical arguments, we are arguing that as activity coefficient is a measure of non-ideality of the solution, because in low concentration, there is no ion-ion interaction, or there is limited ion-ion interaction, gamma I has to be 1, or it tends towards 1. We arrived at that just via some physical arguments. There is an additional complexity. When there is no way to introduce a single ion in solution, all the ions, if you actually see, all the solutions are electroneutral solutions. Okay? So there is no way to introduce a single ion in a control one. Okay, so notice I'm talking about in a control one. Okay, so there are there are other technical reasons why something can be charged. Okay, there is something called triboelectricity and so on. We are not discussing such things here. You might have seen this, right? When you have a comb on the fur, okay, this is something which you have seen in your high school. If you rub it against each other, you can get a charged comb and a charged fur. Okay, we are not talking about such situations. We are discussing situation where we can introduce certain species in a controlled manner. So there is no way you can introduce a single species, charge species in a control map. All you can introduce is a salt, which fully dissociates. In this case, we are assuming that at the concentration which we are discussing, at this particular charge has a cation and an anion of these charge states, Z plus and Z minus. These are the stoichiometric coefficients. Okay, so for example, if you have CuCl2, okay, then mu minus will be 2, okay, and so on. Okay, so this stoichiometric coefficients, which you must have again seen in the previous classes. So we can only introduce such a salt, and that salt we assume that it fully dissociates into the solution. So there's no simple way of, there's no controlled way of introducing either a anion or a cation into the solution. So we can discuss the activity of the salt. So we write the activity of the salt in this manner: activity of the cation, activity of the anion, raised to these exponents. Okay, just to simplify the notation, we have substituted that by this quantity. This quantity is substituted along or by this quantity. Again, with some further simplification, we introduce what is called the mean ionic activity of that salt. We say this the mean ionic activity to the power nu. Nu is mu plus and mu minus. You add both these terms, that is mu. And we write the mean ionic activity as this product. This is the same as this product. With this definition, we can write, this is the activity coefficient. We can write the activity coefficient in this manner. This is the fundamental definition of the mean ionic coefficient of the salt. It has two components, anion and cation. This is the activity coefficient of the cation and anion. As I said, you cannot quantify this experimentally as separately as anion and cation, although some theory, some simulations can be done where you introduce just the anion and just the cation. Okay, so even when you do that, there's no corresponding experiment to compare just that experiment. You can only compare when you have both these gamma plus and gamma minus. Okay, so only when you have both of them, you can have a model for the mean ionic activity coefficient. So again, when we simplify all these things, we get this quantity. So these are all not too complex simplification. All I'm trying to state here is that it is impossible to get the activity coefficient of a single ion. Okay, that is, anion and cation cannot be obtained in isolation. They have to be obtained only via introduction of a salt. So all the models that you build, we'll look at one particular model at least, and the experiments you do correspond to obtaining the mean molar activity coefficient. That is this quantity, okay? This quantity, gamma plus minus, that is this quantity. It can be obtained as a function of ionic strength. We'll define what is ionic strength in a later slide. But for now, it's a measure of concentration of the salt in the solution. So we can get this only for a particular salt, not as just cation and an anion. Okay? But we can get some indicators. Okay? For example, if I get mean ionic, this quantity for NaCl and another salt, sodium iodide, let's say, with such kind of experiments, I would be able to get a measure of what is the ionic, that is this particular quantity, for what is the molar activity coefficient for the anion and cation separately. Okay, there are some experiments that are possible. right? So just to get a closure on this topic, all you have to notice is that this is obtained only for a particular salt. Let's also notice another point. When the concentration decreases, because ionic strength is a measure of concentration, mean molar coefficient tends towards 1. Right? That follows just from these definitions. Okay. So, and from this kind of physical arguments anyway. All right. So, okay. Let's move on. The last quantity which is of interest to us in this electrochemical class is the activity of an electron. Okay. So we are going to define the activity of an electron in the following manner. This is the potential of that at that particular, let's say this electron is present in a metal. That is the electrochemical potential of the electron in that particular metal. And this is some reference value. Okay. So we have discussed that this kind of, for a single electrode electrolyte interface, you cannot measure what is the potential that exists at that interface. We can only measure the activity of an electron with respect to the activity of the electron in a reference system. Okay, so the usual reference system we utilize is the activity of the electron present in a reference electrode. It may be standard hydrogen electrode or calomel electrode or some such reference electrode. So with respect to some particular electrode, we can talk about the activity of the electron present in your working electrode. Okay, the working electrode is the electrode of interest. Okay, so if you have two phases of similar composition, let's say I have one platinum electrode, which is part of a standard hydrogen electrode, and the other electrode is your another platinum electrode, which is the working electrode, supposing I'm studying hydrogen evolution reaction. Okay? So then these two phases of the electrode are the same, both are platinum. Okay, there can be small changes in what is being absorbed and so on. For in such a scenario, we can define the ratio of the activities. I mean, there's a typo here. Okay, so there's a equal to that is missing here. Let me see whether I can fix it. Yeah. So we can discuss the ratio of activity between the two electrodes in the following. Okay, so supposing I make a voltage measurement between these two electrodes, I can, with such a voltage difference, I can discuss the ratio of the activity of the electrons in the two electrodes. Okay, so here I emphasize that both the electrodes have same or very similar composition. We will address this issue at a later stage. What happens when you don't have two electrodes which are same composition? Okay, that's an additional complexity. But when you introduce a topic, we will not introduce all the complexity associated with that topic. Okay, that would be the philosophy of this course. Okay, we'll take a first cut and then go into a particular topic in greater detail in subsequent lectures. Okay, let's move on. So we have wrapped up, okay, with this slide, we have wrapped up discussing how do you define activity in different scenarios. We discussed 3 scenarios. One was gases. Then there were liquids. We placed a lot of emphasis on solutions which have ionic solutes, and then we discussed electrons. Okay, so ionic solutes and electrons are most relevant to discussion of electrochemistry. Then this is a phenomenological theory. Okay, so right now we have defined the terms. We have not yet given a model for discussing activity coefficient at different concentration. Okay, that is the agenda for the rest of this lecture. Okay, so we'll only address a part of that agenda. We'll see which part. Okay, but there is certain aspect of model building which is very important. That's what I will emphasize. This model for obtaining the activity coefficient is called Debye Huckel theory. It's a very interesting model because not only it is interesting in this context, this model building has certain pedagogical relevance to a variety of contexts. Okay, so whenever you see such a model, it is not just enough to understand how this particular model works in this particular context. It's useful to glean some skill set on how do you build models in general. Okay, so this is one, we'll take this case as an exercise in model building. Okay, so, okay, what is that we are looking at? So we are looking at interactions between ions in solution. Okay, so these are the solute ions. These are not ideal in many instances, because of many reasons. One is that they're interacting strongly because electrostatic interactions, even when you have a dielectric solvent, they are still long range. Therefore, they interact with each other. There can be attractive interaction between these two, let's say, and there can be repulsive interaction, okay, between these two, for example, let's say, okay. And then there is also another interaction because of the finite size, okay, and so on, okay. And there can be some structure associated with this region surrounding the ion, okay. So there are different reasons for non-ideal behavior of the solute, ionic solute in this case. How do you model these non-idealities? That's the question. Okay? So if you can model the non-ideality, we will succeed in getting a model for activity coefficient. And if you remember, the electrochemical potential depended not only on AI, activity, which in turn depends upon activity coefficient, it also depends upon phi. Okay? What is the electrical potential that is of relevance in a solvent? Okay? That is the other term. So we need a model for phi, and we will need a model for gamma. Okay? I would emphasize the model on phi because this model for gamma I is more to do with electrostatic. We'll also just touch upon. Okay, so let's get started. Remember, this model was proposed by Debye Huckel in 1923. Okay, this is just before the revolutions in quantum mechanics. So at this time, lots of interesting experiments were done from late 1800s by Faraday and many others in Europe. So, but many of these things were not, I mean, the properties of ions could not be documented in great detail at a molecular level because the modern analytical techniques, okay, were not available in those times. So you should note that it was done in early 1900s. Okay, so how did they think about this? Okay, this is, so I want you to take this case study as an exercise in model building. Okay, let's see how do you build a model in this. Let's look at the physical picture first. Supposing you have a positive ion, intuitively you would think that around a particular positive ion, there will be more number of negative ions on an average. Okay, so for example, if I draw a sphere, okay, in this case, in the 2-dimensional, represents a circle. If I draw a circle around this cation, I have on an average more number of anions surrounding the cation. Likewise, if I draw a circle around an anion, on an average, I have more number of cations. Okay, that is one observation. So the way Debye Huckel thought, these are two different people, okay, thought through this model is that they decided to focus their attention on a particular ion. Let's take this as a positive ion, which has a particular radius A, okay, of a particular radius A. And then what they did is, instead of giving identity to different ions in solution, these ions are at a particular spatial position at a particular time, right? But they are also constantly moving around because of the thermal energy they have. They're just not fixed. There's not a rigid lattice. This is a liquid, okay? So they are moving around. What they imagine, okay, in their mind's eye is that they imagine a particular ion and the rest of the ions surrounding this ion to be smeared in the medium, okay? The identity of these ions are lost. Only the reference ion have a particular identity. All these ions are smeared out. How are they smeared out? They're smeared out in an interesting manner, okay? The overall charge in this medium is neutral, right? So if this medium has, if this particular ion has a charge Q, if I integrate the value of the charge in the rest of the medium, because the overall solution is neutral, if the integral of the charge in the rest of the solution should be negative Q, okay? So that's the way I've smeared the charges, okay? All right, let me repeat it. So as the entire system is neutral, okay, if I give identity to a particular ion, and I give, let's say, positive charge Q, and I integrate all the charge other than this charge, I can state two things. One is that if this is positive, if the reference ion is positive, the integral of the rest of the ions, the charge of the rest of the ions should be negative. And not only that, because the entire medium is electroneutral, it should be negative. This way of smearing, okay, of a particular ion, seeing an average field, is called a mean field model. Okay, this is a powerful technique in physical theories. Okay, so the mean field model was the dominant way of building models in molecular sciences and many other fields of science and engineering, chemistry, and so on. This is one example of a mean field model. Okay, so what is the field here? When I, as a function of, when I change the spatial coordinate, okay, when I change the spatial coordinate, I can associate certain field variables. The field variables can be potential, it can be gradient of potential, it can be charge density. Okay, so I can define a continuous variable. The field variable is a continuous variable because I have coarse-grained the system in such a way there is no identity of ions in this region. Okay, I only have a field variable. As a function of the field variables, I can define certain quantities. We'll see what are the quantities I'm going to define. So this is a mean field model. This ion is going to see an averaged field surrounding it. And then I'm going to utilize the laws of electrostatics to capture the energetics. Okay, it was done in 1923. By then, all the Maxwell's equations were well documented. And two equations of electrostatics would be relevant: Poisson equation and the Gauss law. Okay, we'll see that. And then we should go beyond electrostatics. Okay, so I've always emphasized the potential which you see in electrostatics is a mechanical potential, but the electrochemical potential is a thermodynamic potential. The electrostatic potential doesn't have temperature in it. Okay, so it is a mechanical potential, but electrochemical potential is a function of temperature and pressure and mole fraction. So we will introduce something called Boltzmann distribution. You can see what that is in the next slide. So this Boltzmann distribution brings in the aspect of temperature into the model and makes us move from a mechanical potential to a thermodynamic potential. And then you'll see another mathematical trick again and again in many models. One is how do you, this trick is called the Taylor series. We will compare two quantities, called one quantity B small compared to some other quantity. Therefore, you can represent an exponential by a power series, which will enable you to solve the problem analytically. Because again, notice this was done in 1923. There were no computers, okay, in those times. So just to emphasize, this is a case study in mean field modeling. We are going to use our intuition on electrostatics to capture energetics. To bring in temperature, we are going to use Boltzmann distribution. And to solve the problem analytically, we are going to use Taylor series. Okay, this is the algorithm for Debye Huckel theory. So let's do one by one. What is the role of electrostatics? We know from electrostatics, my Poisson equation, I can write it in the following. Okay, this is the charge density. I am looking, my reference system is here. Okay, so I am having a charge here. I want to solve the electrochemical potential in this field. Okay, so I can define the field. And I can define, let's say I'm defining a field here. Okay, so if I'm drawing a sphere here, like I would use in a Poisson equation, that would depend upon del squared phi will depend upon the charges that are present, right? So that will depend upon rho I, right? So that's where the connection with the electrostatics is made. How do you get rho I? Rho I is a function of concentration of different species that are present in the solution. Okay? So rho I can be written as sum of Zi is the charge on each ion. It can be positive or negative depending upon whether it's an anion or a cation. I can write del squared phi as at that particular point as a function of this quantity. Okay, so rho I is a function of sigma of Zi Ci, right? All right, what would be the boundary condition? Again, if I have R equal to 0 as my reference ion, and as I go far away from the ion, then because the electron neutrality condition, my potential will be 0. Okay? Because this is a second order linear equation, I need two boundary conditions. What are the two boundary conditions? One would be as I tend to infinity, my potential will be 0 because just of electron neutrality. And then at the radius of the reference ion, I can use electrostatics to get a sense for what would be d phi by dr. Okay, just from electrostatics. Okay, so I know the charge of the ion, and then from electrostatics I can compute what would be the potential. Okay, so this is again both are from my electrostatic principles that I am aware. Okay. All right. Then this is Poisson equation. The second law I would use for electrostatics is the Gauss law. So Gauss law, again, you must have revised your electrostatics. So what I can get from Gauss law is that I can convert a volume integral to a surface integral, right? So amount of charge present in a particular volume, I can integrate that. And supposing I'm integrating that for the particular reference ion, I'm integrating the charge in the wall over the volume of the reference ion, I would get ZC, that is the charge of the reference ion, times Q, right? That will be the charge of the reference ion. I can convert that into a surface integral using the Green's theorem, which is also the Gauss law in this particular instance. Green's theorem is a more general mathematical theorem. When I apply to Gauss law, I'll get this expression. Okay, so I will get this is the area integral, and then I would get the epsilon electric field ds. Okay, so this is the knowledge of electrostatics that I am utilizing for modeling the system of interest. All right, where does thermodynamics comes in? Thermodynamics always comes in via the temperature, right? So let us understand this expression intuitively. Okay, this is called the Boltzmann distribution. Boltzmann distribution, Maxwell Boltzmann distribution also. We'll see what is the meaning of this distribution. Okay, so what is that I'm trying to quantify here? I'm quantifying the concentration at a particular point. Okay? The concentration at a particular point can be given by two quantities. That is Ci infinity. That is the concentration of that species at infinity, far away. Okay, so far away, as I said, that the concentration, the potential far away is phi equal to 0. Okay, so just from this condition. Okay, at a point where the potential is 0, we call that infinity. The concentration of that species is Ci infinity. So it is the concentration at that particular point is product of that quantity, which is a constant, times this quantity. Okay, this quantity is the work required to bring the ion from phi equal to 0, that is at infinity, to that particular spatial position. Okay, at that particular spatial position where I want the concentration, that is Ci xyz, let's say. At that particular xyz, the potential is phi. Okay, potential of the solution, electrochemical potential of the solution. Phi, the potential is phi. Okay, phi is a field variable. Phi is a function of xyz at that particular point. So this is the energy of ion at that particular point. Okay, so the energy of that ion at that particular point depends upon the work I need to do for bringing the ion from infinity to that particular point. That would be dependent upon the potential at that point times the charge times the Faraday constant. This is just the work done. Okay, so this we have done in the earlier lecture. Divided by RT. Okay, so I'm not deriving this. This is from your thermodynamics, statistical thermodynamics class. So that is the way to express this. Okay, but let's get a feel for this. Okay, so if phi I is 0, okay, then the concentration would at that particular point will be same as the concentration at infinity. Okay, that also makes sense. Okay, if T is very less, okay, that means when T is very less, this quantity will be a large number. Okay, the difference in concentration between infinity, where the potential is 0, and at your particular location would be a lot more if T is very less. As T increases, that is the thermal energy increases, and increase in thermal energy goes towards smearing the ion in the solution. Okay, so that's what temperature does. If there are more questions, I hope there are more questions. We can address them in the discussion session. Depending on the questions, I can elaborate certain other specific points. You can also look at what is there in your text. Okay, so I have given the value of Ci. Why is Ci needed? Because I need to get Ci for plugging in rho r, right? So because I have spherical symmetry, because I'm looking at ions, I can convert the differential equation into spherical coordinates. I can just plug in uh, the Poisson equation, spherical coordinates, and Ci, which I obtained from this expression, into the Poisson equation. Then comes the mathematical approximation. This is a very important approximation that you will see again and again. Okay? So if whenever this quantity is relatively small compared to RT, in fact, this is a condition for building a mean field model. Okay? Mean field model is measure of two energy scale. One is the thermal energy scale, which is RT. Okay, that is the energy from equipartition theorem. Okay, RT is the energy in each degree of freedom is half kT, right? So that's what you see from your equipartition theorem. So that is the energy scale available from due to thermal energies. Okay? Because T is a measure of average energy present in each degree of freedom. RT is the measure of thermal energy. The other energy scale is that your electrostatics or electrochemical energy scale that is given by this energy scale. Unless this energy scale is relatively small compared to this RT, you cannot build a mean field model. Okay, this varying is possible because the potentials do not freeze each ion in that particular point. Okay, the ions can move around. You can build an average field because this is relatively a small quantity compared to RT. Okay, I've probably used a lot of words. I'm sure there are questions. We can address these questions in the discussion session. Okay, so whenever this is true, when this is small compared to this, I can use a power series expansion, Taylor series expansion, to represent the exponential. I can represent this just using two terms. I can linearize this exponential via these two terms. This is the only way I can solve the problem analytically. Okay, remember this was done in 1923. Okay, when I substitute this into the Poisson equation, I can get a constant. This constant is called the Debye length. Okay, the Debye length is given by this expression. Okay, I put this into the Poisson equation. I can rewrite this equation using this. This expression is called Debye length. Let's understand the meaning of this quantity lambda. Lambda is given by ratio of this by this. Okay, let's understand the meaning of lambda. Okay, when would lambda be large? Lambda will be large when T is large or when Ci, this quantity, is small. Okay, what is this quantity? This quantity is called ionic strength. Mu is called ionic strength. Mu I can rewrite using this expression I've written in terms of mu. This is called the ionic strength. This is measure of average concentration of the ions in solution because this is Z squared. Okay, both anion and cations will contribute equally. Okay, so will contribute to the ionic strength. Larger the ionic strength, there are more ions in the solution. So when lambda is larger, ionic strength is smaller. That means I have a lesser concentration of ions in the solution. Okay, that's when the Debye length is larger. It can also be larger when T and hence RT is greater. That is, the thermal energy available is larger. Okay, let's visualize this pictorially. Okay, so I have an ion and then I have some Debye length, okay, which is a measure of screening in this system. Okay, we will look at it more quantitatively. This Debye length around this ion, okay, this is a length scale around this test ion. It will be larger if my thermal energy is larger, or when ionic strength is small. Okay, and again, I can have the converse. When lambda is a small quantity, that means my ionic strength is large quantity, or when RT is a small quantity. Okay, let's go on. So I'm just defining what is lambda from just rewriting this equation in the following. Okay, okay. What is the solution? The solution for the Poisson equation in the solution is the following. Okay, so I will get del phi, that is when I solve the Poisson equation, I can get del phi for the medium. I'll get the solution using the Taylor series in the following. Okay, so let's contrast this solution to a system for which I have some intuition already. Okay, what is that solution? I have an intuition, I have a mathematical formula for del phi for an ion that is present in vacuum. What is my solution? That is Q by 4 pi epsilon r. Right? That is my del phi for an ion present in volume, vacuum. Okay? Compared to that, my solution has an additional component. Okay? The additional component is an exponentially decaying part, which is scaled in such a way, R is scaled by this factor, lambda, which is the Debye length, which depends upon thermal energies as well as the ionic state. Okay? So as opposed to a bare ion in vacuum, I have another term which decays in exponential manner. Okay? So let's go further. Let us look at just the solution for phi itself. This is dou phi by dou r. This is just phi itself. Okay. So the solution, when I do mathematically solve that, I would have this quantity. This is the charge on the cation. All the rest of the terms are straightforward. And then I asked to build some intuition on this term. I asked what is the phi at 0, okay, in this medium. Okay, so to get that, I am going to get phi at 0 in the following manner. Okay, so I'm going to keep reducing A, asymptotically get that to 0. So I keep on decreasing, bring that A to be smaller and smaller. And also, as I do that, I'm also going to reduce R. And then with that two limits, I'm going to ask what is phi at 0. When I do both the things, A tending to 0 and R tending to 0, what I see is that phi at 0 is this quantity. Okay, it's a constant. All these things are constant. There is Q, lambda is a constant. This is the property of the medium, right? Dielectric constant and so on. Okay, so I can get the solution for phi at 0, and I can also talk about phi as a function of R. Okay, so this is phi as a function of R. So I can also put this into this. I can discuss phi of R using that particular term. Okay, so let's put all these things together and look at some other field-dependent quantities. Where did I start? I wanted certain field-dependent quantities. The quantity of greatest relevance is the potential that is present in the medium as a function of distance from the central line. Okay, so it is a function of two, a critical quantity. Okay, one of course is the distance from the central line. Another quantity is the Debye length. This length, okay, if it varies, okay, what is the variation? Here I have shown two variations. One is if the Debye length is 1 lambda, or the Debye length is 10 lambda. If the Debye length is a smaller quantity, when would the Debye length be a smaller quantity? Okay, so go back to the definition. Debye length will be a smaller quantity if the ionic strength is greater or RT is a smaller quantity. Okay. If that is so, my potential will vary more steeply. Okay. If the Debye length is a larger quantity, that is, if I have a more dilute solution, my Debye length will be a larger quantity. If my Debye length is a larger quantity, the rate at which the potential decays from the central ion will be it will decay in a less steeper manner. If you have a more concentrated solution, the decay will be more steep. It will be less steep in a less concentrated solution. Okay. Okay. So again, look at the feature of my decay. Okay. So I had, if I go to electrostatics, I had the decay as 1 by R decay. Okay. But here, in addition to 1 by R decay, there is another term which is an exponential decay. There is a 1 by R term which is like electrostatics. This is what I would have gotten just from ion and vacuum. Okay. But as opposed to that, I have an exponentially decaying term. When I couple both of this, I have the potential decaying in this manner. All right. So just to emphasize, lambda is given by this quantity. Okay. So just there is one additional topic which I'm not going to elaborate in this lecture. Okay. There's just because those are just concepts from your from your electrostatics, which I request you to go look at your electrostatics books and get it. Okay. So what are those terms which you get from electrostatics that is of relevance here? Okay. So here if you remember, when we started with two issues. One is that we wanted the magnitude of one field variable, which is the potential, for which we have obtained the solution from starting from Poisson equation. The other term, if you remember, is that the electrochemical potential depends upon free energy changes. Free energy changes depends upon work done. Okay, what is the relevant work done? There are two quantities relevant to work done here. One is I have what is called self-energy. I have, let's say, an ion of particular charge. I have charged it to a particular value Q. Okay, so the way you would think about that work done in electrostatic is that I start a spherical ion with Q equal to 0. Okay, and then I charge it by adding small charges, infinitesimally small charges to the central ion. Okay, so I build the charge of an ion from 0 to a particular Q. Okay, when I do that, my potential also changes. Okay, with the changing potentials, I add more and more charge. Okay, that term is called the self-energy term. And then there is an interaction of the ion with all the rest of the ions in the medium. Okay, so these are both electrostatic terms that I have not elaborated. Once I have these two work terms, I can connect the work term to the free energy changes. Once I have made that connection, I can connect the free energy term to the activity coefficient. When I do all those things, that part I have not elaborated in this lecture. It's also not elaborated in this two textbook, but what is a very good reference for understanding that term is the physical chemistry by textbook of physical chemistry by Castellan. Yeah, so I've added the reference here. So this is an excellent physical chemistry textbook available as an inexpensive Indian edition. I would encourage you to go and buy it and read how you get this term so that you can complete all that is relevant to Debye Huckel theory. Okay? Because once you get the work term, you can connect it to free energy change. Once you have the free energy term, you can connect it to activity coefficient. When you get that, you can compare what you get from your model to what is being measured from experiments. Okay, with that, you can get a closure on Debye Huckel theory. Again, Castellan has an excellent discussion on Debye Huckel theory. I would encourage you to go and read. Okay? I mean, that would take even more time because of the constraint we have on the number of lectures available. I'm not going into how do you derive this term, but Castellan has the derivation. Please go and refer to Castellan for getting an idea of this term. All right, so we will wrap up, and in the next lecture, we will look at the structure of double layer in the electrode-electrolyte interface, and we'll get started on electrochemical kinetics. The most fundamental equation relevant to electrochemical kinetics is called the Butler-Ohm equation. We will look into that in the next lecture. Thank you.